Good morning.
Hey, good morning.
Thank you for showing.
Morning. Cheers to Monday.
Let's see. What are we doing?
Let's do that calculus with
Share
that
screen.
those polar coordinates.
Talk about a little polar calculus. And today we are going to tackle the last part of this, which is finding the area of these cool things. And so when we last left off, let's see here, we were looking at this cool curve, 2 + 3 sine of theta, and we answered 2 questions last time that calculus adds to just the fact that even these amazing cool polar graphs exist. Remember, this is all based on the concept of just changing how points are defined. Instead of giving an x and a y coordinate, we're going to give an angle and a radius to get to a location, kind of more like navigation. So just changing that alone made these really neat style graphs as a result. And we said, well, these are cool graphs. So what does calculus allow us to do besides graph it? Well, it allows us to find some cool things like what's the slope of the curve at any given point. So Thursday, we talked about how to find the slope of this at a number of points. And we said the interesting places to find that slope might be up there at the top where the slope is horizontal, or over there on the left side where the slope is vertical. And we found a really kind of a surprisingly crazy formula for the slope. And then we ended Thursday looking at the arc length. In other words, how to find the distance that would travel, which again is a remarkable thing that you could figure out. And today we're going to look at how to find the area of that. And before I do that, I did post this in my open math for you. But this is going to be the note sheet that you're going to get for the next test. And we have now gone far enough into this that you realize, wow, there's a lot of stuff that we've built for ourselves. And so we did a bunch of things on parametric in terms of finding arc length and area under a curve and slope. And then we did polar and how to convert back and forth from polar to rectangular. And then the stuff I was just talking about. Remember how complicated the slope formula was? Wow, what a crazy formula. And so that's kind of cool. And we said that, well, if the top of this was equal to 0, then that would make the slope equal to 0. So we said, hey, that'd be a horizontal slope then if we just let the top equal 0. And we said, well, if the bottom was 0, then the slope would be infinity. And if the slope is infinity, then that would be a vertical slope. And so we were able to find particularly interesting slopes as opposed to just random ones by saying, hey, at 3 seconds, what's the slope? Time is 3 or something like that. If it was in, I guess I'm saying that more like it's in parametric, but in this case, if we said the angle is at 20 degrees or 1 radian or something, what's the slope there? Just some random spot. But it's kind of cool if you're trying to graph this thing, at least without the technology that we have, it'd be kind of cool to know where the horizontal and vertical slopes were. So we found all those, and we found going out the door, the arc length of that shape was around 21. And now we're going to look at the area. Notice what a crazy formula the area seems to be. What? Well, let's go talk about that. So I point this out just because you might want to start kind of, I don't know, perusing through that note sheet just so it's speaking to you, so that when the test day comes, you're familiar with it. So, new note sheet. And so what is this, 12.3, I think, 12.3. So here's the deal, polar calculus. If you're finding the area of some weird shape like this, let's just do a little bit of theoretical background to this, just so you have a sense of kind of why this works. So maybe your graph takes off and kind of starts doing something crazy like this or whatever. It turns out to be kind of difficult, especially if the graph, kind of continues down here and so forth. It turns out to be difficult and inefficient to break this thing into rectangles. So in the past and everything we've done before, we said to find the area under a curve, we'll just break it into infinitely skinny rectangles and add them all up. That's the theory behind integration and so forth, how to find the area under a curve. And so that would, that would work here in a sense. But because these shapes are not defined by X's and Y's, does it make sense? This height is a Y and this, width is a tiny bit of X, change of X. Since this curve is not defined with X's and Y's, that makes this process rather difficult. And so in polar calculus, what we say is, well, how about if we did this instead? What if we, as we jump from, say, here to here, rather than make a little rectangle out of that, or even a trapezoid or something like that, what if we actually made a chunk like this? So what would that be? How would I figure out that? And then when we move to the next location, if you will, then we say, okay, now we're going to bump up to here. Well, then we'll have another one of those kind of same exact areas. You may remember that in a circle anyway, those little dudes, those little pie shapes are called sectors. It's like a chunk of a circle. But this isn't a circle, right? That's the thing that's kind of a problem. Is this is a polar graph a circle? Well, not very often. I mean, occasionally it is, but it's not really a circle. And in the same way, when we took a curve like this and we, made a rectangle under it, it's like, is that a rectangle? No, not unless you make it really skinny, right? If you make it really skinny, then you could say, well, a rectangle would work for that if it's infinitely small. And so the principle here is really kind of the same idea. So even though this is not a circle, we can still treat it like one if those spaces are really small. In other words, we define this angle right here is not just theta, but a tiny amount of theta. If theta is like 5 degrees, then this is not a circle and it's not going to work at all. But if theta is like 0.1 degrees, 0.01 degrees, then that little shape out here could be considered to be circular. And so what we'll be doing then is adding up those sectors. And so, in the case we picked rectangles in the case before and everything we've done in the past, just because rectangles have such an easy area. Well, what's the area of a sector though? And you may have some, memorized answer to that question, but let's just build that again really fast. In the case of a circle, so if I pick some chunk right here, and you wanted to find some area like that, again, that is a sector, really a sector. This is sector-ish up here, but that really is a sector. So how are we going to find this? Well, it's just a chunk of a circle. The area of a circle. The area of a circle is pi times radius squared, you would say. But this is just a portion of the circle. And all you have to do is set up, well, a proportion. That angle is part of the whole angle of the circle, just like that area is part of the whole area of the circle. So I could say theta is to the entire angle of the circle what the area, we'll call that area of sector, area subscript S. So the angle is part of the whole angle, just like the area is part of the whole area. Does that formula make sense? So then if I solve for the area of the sector, hence the area of the sector, and notice how cool it is, by the way. This is, again, one of the other places where you learn that radians are the natural way to measure angles in the universe. Again, it feels backwards to me, even though I've taught math for 29 years, it still feels wrong. I still think in degrees. But if I put 360 down here, because that's the entire angle in the circle, then the beautiful thing that's about to happen won't happen. But if we say no, the entire angle of the circle is 2 pi, then since the area of a circle involves pi, that's kind of why it's the natural angle of the universe, if you will. That formula doesn't say 180 degrees r squared, it says pi times radius squared. So if I solve for that and I multiply pi times radius squared away so that we solve it for the area of the sector, then notice the fact that I put pi's in it allows those to cancel out, which they wouldn't otherwise. And so the area of a sector, we say, this is the thing you might have had memorized, is that lovely little formula. However, it has the caveat that theta is in radians. You see how that's not going to work? In other words, the angle had to be radians, because you can't say over here, you know, like 24 degrees is to 2 pi. That doesn't make sense because it'd be thinking it was radians. You could say 24 degrees is to 360 degrees and it would work. But that angle of there's got to be in radians for all of this to happen. So that formula is kind of cool. So maybe that's running around in your head. Well, that's what we're going to do. So notice that formula, if you will, kind of matches what we're trying to do, which is to do things in polar. Notice it has r's and thetas in it. And so we're going to say, great, I know how to find the area of a sector as long as I make that theta really small. I'm just reminding us that this is a really small angle. Then we can actually treat this little curve over here as an arc. And again, an arc is not just a random curve, it's a chunk of a circle. So we're just going to add up sectors this time in this world. And if we add up all of them, as many as we want and as many sections as we want, then we got a formula. So we say, great, well, let's just add up all the sectors. Remember that I'm going to erase this, but remember you used to say, hey, if I chunk up underneath a shape like this and I'm going to make a rectangle, we said, well, the height of it is y and the width of it is a little bit of x. And so, hey, the area of that is y times dx. There's the area of my rectangle. And then the sigma notation is, I'm sorry, the summation notation is add them all up. There's a lot of them. So we're going to do the same thing. I guess I don't need to erase that. Except for we're going to say, hello, Ben. Thanks for showing up face to face. And I feel like there are 2 people in class with me. We're going to say the same thing, except for we're just going to say, we're adding sectors, not so. What's wrong? What's wrong with this formula if this is an integral? Take a look at that formula for a second. Let's go back and look at the note sheet that I gave you. Why? What's the deal? Like that doesn't look quite the same. Like what's?
You need a d theta.
So I see the 1/2, but then there's like, it was 1/2 times theta times r squared.
Not everything's
What's your
in
thoughts
theta.
on that?
The radius is not going to have a theta in it.
Well, remember, in order for this to work, didn't that have to be small for one? And then secondly, notice we have 2 different letters here. We have theta, which is kind of one variable, and r is another variable. If I change the value of theta, then I get a different value for r. But remember, we said that r was a function of theta. In other words, isn't that the way all our equations are written? Like r equals sine of theta or something like that. In other words, I can rewrite that. In other words, this r is some function of theta. So in other words, this statement could be, I guess, more clearly written or more practically or more usefully written if I said f of theta, and I'll write it correctly this time. I don't know where to put the squared when there's so much stuff going on. That's a terrible looking theta. Let's fix that. So there's the 1/2 r squared, and then there's a tiny amount of theta outside. And so, okay, that looks like a normal integral. There's a little dx. Hey, look, remember there was a dx out here. That actually was really important that that was out there, because that's actually the width. And it's very important that that be tiny. Anytime I see d, it's telling us it's tiny, infinitely tiny. As a matter of fact, it's nothing, it's 0. So this will be an arc as long as that angle is really tiny. But again, it's got to be there, right? That angle's got to be in the formula, otherwise we don't have an area. So now we're ready to rule. This is how you find the area. This is the recipe for finding area in polar. That's cool. So just for the fun of it, let's just try this out on something really simple, like something you already know. Do you remember the other day when we looked at kind of the best equation of all in polar, which was a circle? Remember how ugly circle equations are, or hard to kind of work with in rectangular? But in polar, we said all you have to have is like a radius. If you just say r is 6, the radius is 6, and notice there's no theta in that formula. It doesn't say 6 times theta or 6 times the sine of theta or something like that. There's no theta at all, which basically just means the ordered pairs, as long as they have r as 6, as long as the radius is 6, we don't care what the angle is, can be anything. Can you visualize how that would form a circle of radius 6? Okay, well, okay, what does this formula say? Well, we already know the area, kind of the old way. The area is equal to pi times radius squared, or pi times 6 squared, or 36 pi. So we know the answer to this is 36 pi. But would that work kind of in this world? You may be thinking, no, I'm not really seeing it. Well, wouldn't it be the integral of 1/2 times the function? In other words, whatever the function is in terms of theta, that's what you stick in here. Well, ours is the simplest one of all. It's just 6. Like, that is our function. It's 6. And I don't have to do anything to it. It doesn't say derivative or anything like that. I just have to square it and integrate it with respect to theta. Well, 6 squared is 36. 36 divided by 2 is 18. So this is like the integral of 18 with respect to theta. But what are the limits of integration for this circle? Like, if I'm sitting here saying I want to know the area of this circle, through what's our unit here? Oh, degrees or radians, or an angle. Through what? What's our angle in order to get an entire circle? Do we say we want to go from 0 to 2? What do we do?
0 to 2 pi.
Well, if our circle is out here at 6, we got to go all of the, notice we started at angle 0, and then it gets up to pi over 2, and then down to pi, then down to 3 pi over 2, back to 2 pi again. It's got to go all the way from 0 to 2 pi if it's actually going to make an entire circle. Do you agree with that?
Yeah.
Now, what's cool about this is we don't have to make an entire circle. We can make a chunk of a circle, and this formula would work really well. Whereas it's a little tougher kind of in not doing this with calculus. Oh, okay. So now I say, great. Okay, this goes from 0 to 2 pi. Since we're taking the integral of 18 with respect to theta, then when I take the integral, it grows a theta, just kind of like, the integral of 18 would be 18x. Except we're working with an integral in theta. And now I just evaluate that from 2 pi to 0. And I suddenly see what I want to see, which is 18 times 2 pi minus 18 times 0. Whoa, I actually get 36 pi for that. Of course I do, because that's the answer that we already knew before we started this. So it's working. Now, in the case of a circle, you'd say, well, that's kind of silly to do that. And you're right. But what about more complicated equations? So let's go tackle one of those. Now it's been 3 days, and so our, the illustration we've been working with is probably a little bit gone for you, but we've been playing around with the example equation r equals 2 plus 3 sine of theta. That was our example equation. Let's go stare at it again because I never erased it. So again, we watched it grow from 0. So if you put 0 in, again, just to think about, can you make a polar equation for yourself? If you put in angle 0, the sine of 0 is 0, 2 plus 3 times 0 is 2. Notice the radius is 2. So when the angle is 0, the radius is 2. So our first point is 2, 0. Great. Well, then what happens if you start choosing an angle bigger than 0? Well, 0.2. So our angle is 0.2. Well, the sine of 0.2 is not 0. It's actually something. And then when you multiply it by 3, it's something. And then when you add it to 2, the radius gets a little bit bigger. And so we're getting a larger radius. And so the radius grows for a while, gets longer and longer. Do you see the radius getting bigger and bigger and bigger? So anyway. So the question here, though, why is this a weird question? If I say find the area of that statement right there, why is that a weird question?
Because there's like 2 areas, I guess. Like there's a little area inside of a big area.
Although if we were to just, since
tell me.
essentially we're taking the area, if we were to untie the loop-de-loop, if you know what I'm saying, wouldn't it just make a circle? So then you could just find the area of the circle.
I put
That
this on
makes
the test.
sense.
Find the area of this. I think this one was a limicon. I can't remember for sure. I think it was a limicon. Yes. Find the area of this limicon. What question do you have immediately for me before you can even proceed?
What area are we finding exactly?
My volume down or something? Not hear anybody talking.
Can you hear it?
Testing.
There we go. I hear you now. Maybe it was me. Maybe I had my volume down. I thought no one was talking.
We've all been discussing your question amongst ourselves.
That's funny. What did you decide since
We
you
basically came up with the issue is that little loop-de-loop in the middle. Like we don't know how to get that area in the center of the circle.
Yeah, notice it's like, what area do you mean? Because, and if you just said from 0 to 2 pi, what area would that even give you? Does that make sense if you, because it took kind of a full rotation of 2 pi. And after this, by the way, if you keep going, it just writes over the top of itself. So it doesn't make a new graph. It doesn't spiral and just keep on going. So, if I say from 0 to 2 pi, I'm not even really sure, what you mean by that. And so this is an interesting question. So for instance, we saw it grow. Let's just start with something kind of simple. We saw it grow from here all the way to here. Notice you should be able to tell where you are right there because that angle is 90 degrees or pi over 2. So if I said I wanted to find the area from 0 to pi over 2, do you agree that this is the area it's going to give you? Notice the circle hasn't been made yet. And notice it doesn't include that little chunk, this little chunk down here in the bottom, that's not included. So just to keep it simple for a second, let's figure that out. And it is going to include that circle, right? So it's really this. Okay, so 0 to pi over 2. So this formula said, what do? We take 1/2, always a 1/2, and then we just square whatever the function is. The function in terms of theta. Oh yeah, the function in terms of theta is 2 plus 3 sine of theta. So I'm just going to square that. So again, what a lot of these types of formulas create, and this is something I'll say very clearly on the test, I might say like arc length created a really nasty formula. And this formula, sometimes because you're squaring some already somewhat crazy equation, I'm squaring it. This one's worse because it's got a square root in it. But a lot of times this will create functions that to take the integral of is pretty painful if we were trying to do it by hand. But let's just think about that for a second. Let's see. First of all, what I wanna, if I had to take this by hand, again, this is really I would say kind of one of the harder questions from Calc 2, which again, you only did like 2 months ago, yet I bet you're kind of going, ah, man, I don't know how to take the integral of that. Would you leave it alone like this, or would you square it out? What do you think?
Wait, we need a 1/2 in front of it, right?
Need a 1/2. I forgot the 1/2. Let's get the 1/2 in there. Thank you. Hopefully, in a
Looks-
sense, if I was alone, I would have caught my mistake by looking at the graph and thinking that doesn't look big enough, you know, or something like that.
I would definitely square it out. So I always like pulling the constants out front. If I could.
So yeah, Connor says, let's square that thing out. Do you find it less intimidating or more intimidating if you squared it out?
More, I guess, at first.
So if you left it back here, and again, I don't want to belabor this point because this isn't Calc 2 anymore, but you might say if you were here, because it's kind of a chain rule problem. In other words, you have two functions. You have sine of junk and you have squared. So when there was junk inside of junk, that was like a substitution problem. So you'd have to let u be perhaps 2 plus 3 sine of theta, or maybe 3 sine of theta. I don't know. But if you let it be 2 plus 3 sine of theta, then you just have u squared, and then it's like, oh yeah, I know how to take the integral of u squared. That's u cubed divided by 3. But the problem is you're going to have to replace d theta, which means you're going to have to get something with du's and d thetas in it. And when you do that, that's going to create a cosine, and that cosine is not going to want to go away very easily. So that's rough. That's tough sledding to find that integral using substitution. It's a little easier down here because isn't the integral of 4 just 4 theta? We love plus signs, right? And the integral of sine is not hard, right? Because let's see, the derivative of cosine is negative sine. So wouldn't it be negative cosine? So isn't this derivative of cosine is negative sine? So the derivative of negative cosine would be positive. Yeah, that's right. And then we get to the sine squared. And it's like, oh man, what do we do with that? Well, you may remember there was a trig identity for that one. Sine squared can be replaced with, let's see, what was it? Let's just have a quick look because I think I still have basic trig identities in here. Oh yeah, it was this one. If you replace sine squared, like if I solve that for sine squared, let's see, what do I get? If I add that to the other side, I think I get 1 minus cosine of 2x all divided by 2 if I resolve that. So if I replace the sine with this, which is not squared, then that's really a 1/2 minus 1/2 cosine of 2x. And then I can actually take the integral of the cosine of 2x. And so you could do this one by hand. But again, even as I said, this is why I teach the way I do. That's been 3 months, and yet, you know, would you be able to get that back on your own? Theoretically, the answer is, oh, you took Calc 2, so you're awesome at this stuff, right? I'd like to keep the focus in this class, you know, more on what we're trying to do here. And so, you know, I might say on a test, for a question like this, just use Desmos or your graphing calculator to get the integral, get the answer. In other words, you're free to cheat from there. That should bother you a little bit because, like, I mean, all you have to do is just write that formula out. Like, we're really not doing anything then. It's like, especially if I don't make you memorize the formula, it's just like stick the equation in there, square it, put it in your calculator, boom, out pops the answer. So that should bug you a little bit. So I could work hard to kind of make up a problem that once you squared it, it wasn't quite so ugly. And by the way, since you're squaring it, does it make sense if I made up some equation like r equals this 3 square root of sine theta or something like that? Because you'd be squaring it, that would suddenly make it pretty nice, right? And so I could make up a problem where you could do it yourself and not have to cheat. I think because I want to get to a number of examples, I'm not gonna continue with this, but I will write this in here because I would recommend you do this on your own time, since this is really 1 minus the cosine of 2 theta divided by 2. Then I actually could take that integral. Now, both of these I actually took the integral. This I just replaced sine squared with it, and I haven't yet taken the integral. So this, as far as what I wrote in the notes, isn't going to make much sense. But let's just cheat. So here's the amazing thing about Desmos, as you know, because I can say, let's see, what can I say? If I go in here and say the integral of from 0 to pi, where is pi? It seems like I should look really quick. Isn't there some symbol for it somewhere? I don't have to look very far for. Yeah, it's right there.
It's right there.
Jeez. This time I've been typing it. So I say 0.5. Let's see, can I just say r? Let's see, can I say r squared? I don't think I can. I think I could say, if I wrote up there, and I don't even know if it would allow this, but instead of r equals, if I said r of theta equals, it might let me do that. But I'm just going to type it in. Theta should also be on this screen, but it is not. Close that parentheses, square it. Take this out of projector mode. It's a little easier to see. And again, it's not working yet because I haven't put d theta there yet. So as soon as I do that, I kind of like that it makes you do that, even though we kind of ignore it, as you know, when we actually carry the process out. So had I left the half out of this, I would have got 24. Like, can you stare at that and kind of see? Yeah, that looks about right. We can't really check it, but does that look like it would be about 12? Let's see, it looks like it has a height of 5. So just roughly, if this thing has a height of 5 and I go to here to 2, 5 times 2 would be 10. But then I'd be adding area I shouldn't have, but then I'd be missing this area over here. So that's more than 10. Like, doesn't 12 seem pretty reasonable? Kind of looks pretty good, doesn't it? So sort of,
Yeah.
must actually be right. That's kind of cool. So if I had to stop to do that, having you guys not correcting me, or you're taking a test and, you know, I forgot the 1/2. So it seems to be working. That's kind of cool. Well, let's do something a little more interesting now. Let's find the area of just that small little loop. What's hard about that question?
I think the bounds would be hard to find.
Exactly. It's just hard to find the bounds. I mean, the equation is identical. Like, all I have to do is just rewrite this thing. I'll put the 1/2 inside just so it doesn't look so weird. Like, done. But you got to find the bounds, right? Well, let's go play around with that. What do you notice about the boundary for that? That's kind of confusing a little bit, perhaps. But would you agree, if you're, if this point is right here, let's see. if you're right there, do you agree the radius is, you know, like 4 and 5 and like the radius right there, the radius is 5. Think about just the radius of the point you're at. Right there, the radius is 2. And maybe right here, the radius is 1. You agree with that? But what's the radius if you actually go bonk right into 0 there? What's my radius right there? What's the radius if I'm at the point 0, 0?
It would be 0.
Yeah, the radius is actually 0. So how could the radius be 0? Do you have an idea? So that's not obvious at all, but basically, because the shape actually, you know, got to here, and then it went up around and then kept going. It was like, it was there twice. Does it make sense? It was at 0, 0 actually 2 times. That's kind of strange. How could that possibly be? Well, the key is just to notice, I mean, that is a radius of 0 right there. If you're at that point. Okay, well, isn't the equation radius equals 2 plus 3 sine of theta? So can't I figure out when that's equal to 0? Yeah, I could solve for theta. Oh, I can figure this out then. I can know what that angle is. You may notice on the note sheet for this that it's not the right one. Did you notice on the note sheet what's sitting right there? What are those? In the language of math, if you see those letters, if you see letters given as Greek letters, what is that implying those are? Those are angles. And so, and that makes sense because it was d theta, right? So we're talking about thetas, angles. So use Greek letters to kind of give people a hint that those are actually angles. Oh yeah, I can see that's going to happen here, isn't it? Because I'm going to solve for theta. So if I subtract 2, divide by 3, I end up with the sine of theta equals negative 2/3. Let's use our brain for just a minute. If the sine of an angle is negative 2/3, then that means negative 2/3 is the y coordinate. So where am I on the unit circle if I'm at negative 2/3? Well, I'd be there. Y coordinate of negative 2/3. So there's one of my answers, and there's my other answer. There's 2 answers to this question, which makes sense on the graph, doesn't it? Because there's actually 2 places where that happens. So in a sense, I think, oh, that's a good thing there's 2 answers. And of course, I got to have my calculator to produce these, because you may remember, hey, that wasn't one of the special right triangles. This is not going to come out perfect. This isn't some nice angle like 3 pi over 7 or, you know, something like that. It's going to be ugly. I don't have any choice but to go inverse sine. I'm in radian mode. Inverse sine of negative 2/3. The calculator produces negative point, I'll just call it negative 0.73, which apparently must be this one, right? Now, remember the other name for that, because we said the graph really existed between, for thetas between 2 pi and 0, right? So there weren't any negative. It's not that that's wrong. I think it would actually work fine if you stuck negative 0.73 in here, but just to help it make a little more sense to us, negative 0.73 can be renamed by adding 2 pi to it. So if I add 2 pi to that number, in other words, add a full lap to it, it's also 5.55. So, or 5.55, that's the one we're going to use. Again, that's not different. It's just a new name for the same thing. And then you should say, well, if that distance right there backwards is 0.73, then that means this distance over here would also be 0.73. Oh, I see how to name this one then. This one would be just pi added to 0.73. So if I say, what is pi added to 0.73, you can get it as accurate as you want, but I get about 3.87. So then we're saying it sort of worked its way over here at 3.87 degrees radians was the first time it got there. And then the angle kept going, and then it got there again at 5.55. So I found myself thinking, really, is that really true? Well, let's go notice this. We'll notice where I was. Look at my angle. It's 3.83 right now, and I haven't quite made it there yet. So this is looking good, isn't it? So I can drag it along and try to stop at 3.87, which is not really going to want to do. I just got it to stop there. Did it really work? No. Again, that's kind of a dub, but I rounded it, right? Like, no wonder it didn't work. Of course it didn't work. It was really 3.87132031. I wonder if it'll let me type 3.871. I think it will, if I remember right. So now it's just a little closer, but it's still not there. Now you might think that's a long ways away, but notice the way the graph is labeled. Each box is worth. So if I take negative 0.73 and I subtract 2 pi from it, I get negative 7.01. Well, that's another name for this angle over there in the fourth quadrant. You're just renaming that one. There's the only way to get the other one is to switch up your thinking. And I like to do this in a way that I can still do 6 months later, 2 years later, which is just draw pictures of it. That's why I think, oh, I went down 0.73 there. I had to logically notice, hey, look, these two have the same y coordinate. And that's what took me over here to say that, oh, well, then that'd also be down 0.3 because it's the same exact angle. And then I just did it logically. I said, well, if I went from here and it took me, took me pi to get there. So I don't like formulas for this stuff because it's different for cosine. If you're a formula person, it's different for cosine, different for tangent. I can't keep all that stuff straight. I just want to draw pictures and figure it out myself.
Yeah. Can you guys see that?
Rad. How fun. That's cool. I know I gave you guys rights to do things like that.
Yeah, that was kind of what I was saying, because it seemed like you went around multiple times, but I was just thinking go 2 and then go. So it would be 2 pi minus 0.73.
Got it.
Would that work?
You're saying to get the 5.55.
Yes, yeah, exactly. Would that still give us that?
Absolutely.
Oh, okay.
Absolutely. Sorry, I totally misunderstood your question.
No, that's fine.
Yeah, so basically what you're saying is to get to this other name, I'm gonna think of it as going all the way around to 2 pi and then I'll back up because I didn't quite make it. In other words, I came 0.73 short. Yeah, absolutely. Which is exactly my argument about why you just reason this stuff out for yourself. So yeah, in the way that you thought of it, you still got 5.55. Love it.
Thank you. I can't erase that last part. I don't know why, but I think you might be able to.
That's kind of fun. I don't really know where that is. It's in another dimension.
Yeah, I think if you have a clear button, you can clear other people's drawings instead of your own.
Well, see, I see it on my screen, but I don't see it on my lap or my iPad. It's not there. That's weird. You erased it before, but you can't erase this one.
Yeah. Is
Actually,
check your Zoom. Sorry about that.
No, you're fine. I'm glad you did that. That's awesome. Not worried about it. Okay, so we say awesome. Well, now I know what to do. I just have to evaluate this from 3.87 to 5.55. Does it matter where you put them? Does it matter if I get them backwards? Is it always like the small one on the bottom, the big one on the top?
It should be, maybe.
Yeah, in this case, I'm wondering, usually if you get them backwards, you get a negative answer. It's still the right answer, but it's a negative number. So yeah, cheat again. So I can go back to, oops, that's not where I wanted to be. I can go back here and just switch these out then, and I know the answer, right? 3.87. Didn't take my decimal point. 87. Backspace. Again, I find myself thinking, is that reasonable? think? Well, the height of it is 1. It goes up 1. And if the height of that thing is 1, the width looks smaller than like a half. So 1 times a half would be a half. Oh, I got 0.44. That actually does look about right, doesn't it? So it's about 0.44. So
Hey, Doug,
yeah.
something is really bothering me, and I've tried to sort it out in my head, but I don't think I'm seeing it. So for this particular problem, normally when we take integrals, you have to have like a plus C, and normally it's negligible. I can't say the word, but normally we don't notice it because it just moves the graph up and down.
Mhm.
But for this, I tried like adding a theoretical constant, and it actually changes the graph.
That is a wonderful
So
question.
what do you do for the plus C?
Yeah,
Because there is a plus C with every, like taking the integral, right?
yep, that's a fantastic question. Notice that once you get done with the integral, you're all done with the integral and you have, 5.55 to stick in, and you have 3.87 to stick in, and you got, we'll just say ugly, there's our answer, and then plus 9, some constant, right? So we said earlier in this class that you could just ignore that if it was what mathematicians call a definite integral. Definite is when we don't just say what's the answer, like what's the formula for all areas, it's what's the actual answer for this particular one. Well, when you plug 5.55 in, don't you get some ugly number with 5.55 in it? And then you have a plus 9. And then you say minus some other ugly number with 3.87 in it, and then there's your plus 9 again. Well, what happens to those 9s? Because that 2 pi's.
Oh, they cancel.
Yeah,
okay.
they cancel. So I end up with 9 minus 9, and so they go away. Yeah, no, so it actually is the same. It's bugging you just because you're thinking this world is different. But once you get rid of the graph and you're just saying I'm plugging numbers in, whatever that constant is ends up going away. So thank you for that bothering you. What if I wanted to find the area of this shape? You do this one. What if I wanted to find the area of this, just this part of it? Like pretend that's not there. That's called a cardioid. But what if I wanted to find that?
Would you have 4 different integrals then?
Yeah, think about that. So Raymond's thinking, would that take 4 integrals to do that?
Or maybe just 3?
Let's see. So I'm just thinking out loud. It's like I want to start from here, right? Like from 0, and then I go around here. And then I get here and I sort of have to quit, right? I got to quit right there, because if I keep going, then it's going to kind of add that. I don't want to go past that. So I want to like quit. And so in a sense, I think Raymond, correct me, Raymond, if I'm not thinking of this right, but you're sort of thinking, well, you could go from 0 to 3.87, and then you have to stop, right?
Yeah.
And then pick it up again at 5.55, and then go from 5.55 back to 0 or back to 2 pi, I guess.
Yeah. I mean, I was thinking of having everything below the x-axis also be another integral, but you could just combine it now that I'm seeing it.
Yeah. So in other words, you said I could go from 0 to wherever this is, stop. and
Yep.
then go from this point to this point, stop, and then go from this point to this point, stop.
Exactly. Yeah.
And the answer to that is yeah, but you don't have to. Why not just go from here all the way to there and stop? So, do you have to start at 0 and take off? No. I mean, if you want to, couldn't you think of this as the start and take off there and go all the way around, and this is the finish? So I'm going to start at angle 5.55 and go all the way around to 3.8. So wait a second, that's the same thing we just did, isn't it? Except for It's like switching these two. Is that right? So let's first, before we do it, let's like take a guess. What do you think the answer to that's going to be? Just like staring at the picture and thinking of it as circle-ish, right? What kind of a number are we going to get? You know, it's like this height is 5. So this is like a circle with a diameter of 5, or, you know, you might think, well, just to make it easier, maybe it goes down to 6. So this is like a diameter of 6. And
I
then,
guess an 18.
yeah, so it's actually 6. It's really a circle of diameter 6, pretty close to it. So that'd be a radius of 3. So 3 squared is 9. So I'm just thinking pi r squared. So pi times 3 squared, so 9 pi. But maybe a little less than that. I'm thinking like 28. 9 times pi would be 28 if this was a full circle, but it's missing a chunk down here. So I'm going to say like 26. Do you agree with that? I mean, you see where I'm going with that?
I'm with Ray. I think it's 18.
What am I doing wrong? You guys both think it's 18. I must be looking at something.
Well, I'm making a square of 4
Fair.
by 4 in the middle, and then I'm adding about 2 more 2 by 2 blocks.
No, I like what you're doing. That suddenly makes me doubt my answer. In other words, you're saying this is 2, this is a 4 by 4 square right here. So we certainly have 16, right?
Mhm.
And then you're thinking, now let's add this and this and this, and maybe some little chunks down there.
Yeah.
Yeah, I like how you're thinking about
Well, the
that.
chunks down there are going to be subtracted, right, from the overall area because it's below the X.
Can't have negative area.
No, but that's the interesting thing about this is we're not finding this relative to this. I'm glad you brought that up because I should have said this sooner. This is not relative to, this is not, there's no negative areas, I guess is what I'm saying, because we're finding the area as a sector. So we're not going to get a negative answer down here. So this is not above and below the, and that's one of the reasons for the brilliance of finding this as a sector instead of as rectangles. Because if we did try to do it with rectangles, that'd be negative. So let's see, this is 1 and this is 4. That's like a triangle. This is adding 2 up here, I'd say. You agree with that? So if this is 16, that'd be 2, 2, 2. So 16 and 6 is 22. And then 23. I don't know. I originally was thinking of it as like a circle, but maybe it's, I'm going to go with 23. 23 sounds reasonable. I don't know. Anyway. So let's see, does it work then if we say we're going to travel from 5.55 up to 3.87 as an angle? Of course, the area of that is 0, right? You're traveling no degrees or no angle. Okay, you guys still see that 2 pi on the screen, right? That's kind of like written on the window somehow. Maybe I can erase that. How do I do that? Oh, I know what you did. You wrote it on the window. I think I can erase that. Goodbye.
Oh,
Yeah, you kind of did it as a whiteboard. So there, do you guys have a little pencil? Yeah, feel free to do that anytime because maybe you don't have the power to erase it. I have to, I'm not sure.
I had the power to erase all the other stuff that was just stuck there. I couldn't do anything else with it.
Interesting. So that doesn't appear to be working because I got a negative area. Why not? Say. Well, the reason that, and did you notice what the answer to that was? Where have we seen that number before? Here's a hint. We saw it right there. Except it was negative. Did you notice that? Well, of course it was negative. We just switched them, right? Isn't that what we said was going to happen? But look at the graph a little more carefully. If you say, I'm going to start at angle 5.55, aren't you right here, but actually here on your way to there? In other words, if you say, I'm going to start at 5.55 and then go to 3.87, aren't you like over here? If you want to start here and go this way, we need a different name for this, because like, isn't this angle 0 over here? So if I want to go backwards, isn't this like a negative angle? We need the negative name for that if we wanted this to work. We can't call that 5.55 because 5.55 thinks it's kind of over here. You see what I'm saying? It's like about to go to here next, if you will. So if we said we wanted to go to 5.55 to 3.87, it actually went backwards around that loop to loop. That's why it didn't give us the right answer, and why it gave us the same answer we had before, but negative. We need to be at, and notice there's like a lot of points that are named this, you know what I'm saying? Because we're hitting the graph a whole bunch of times, but do you agree we're like more like right here? So this is actually backwards a little bit. Well, what is that? Oh, that's the negative 0.73 we got just a second ago. We need to go from negative 0.73 and work our way from negative 0.73 up to 0, and then up to 1 and pi over 2, and then go down here and actually stop at 3.87. You see how tricky that is? So I'm thinking if we put in that, if we replaced the 5.55 with negative 0.73, that we're going to get the right answer to this. Aha. Yeah, that does look reasonable, doesn't it? There we go. So I just did that in the, you know, the laziest way, but to Raymond's point, you could do this in chunks if you want to, no problem at all. And it should add up to that.
So if the graph loops on top of itself, couldn't we go from 5 and then add 3.87 to it to get to the other side?
Yeah, I think so. Everybody understand what Thomas just said? In other words, I think I'm understanding what you're saying. I thought I had it for a second. So you were saying given another name? Maybe I better try that again, Thomas. I thought I had it, but then I lost it.
Right. So if the graph loops on top of itself,
Right.
and at 0 it's 5.55, and then we just add 3.87, it'll go all the way back around to 0, right? But it won't have the little loopty.
Yeah, that's right. So in other words, if we went, I think, I'm still not totally sure I'm understanding your question, but you're basically, I think what you're saying is, if I started from here, 3.87, and kind of went backwards around it, isn't that what you're saying? So
No, if the bounds of our integral are from 5.55 to 5.55 plus 3.87.
gotcha.
Right?
There we go. In other words, 5.55 is right there, is what he's saying. But can't we name that? So we could start from 5.55 and then go 5.55 plus 3.87 to get us back to this spot again. Yeah, I think that would work too. I think there's other
Oh, that
answers.
makes sense.
Yeah, that does make sense. That's a good point. I bet you that would work. Since it loops on top of itself. Love it. Brilliant thought. So let's just to write out kind of what we have and give you a second more to think. So this to me feels like a bad test question, only because it's very hard for me to describe what area I want you to find. Does that make sense? I got to make sure that's obvious. And so let's play with some more examples here, and we'll. So the cardioid portion from, as it turns out, we said we thought it might go from 5.55 to 3.87, but that didn't work. And so we said, oh, we got to rename that to negative 0.73. And then it did work. So cool. Only 26. Again, cheating in Desmos. Okay, well, let's just make up something new now. Let's go try something crazy. And notice if we decide we're going to let ourselves cheat, then we can come up with really kind of fun graphs here and not really have to work all that hard at it. I want to try something really quick here too, just for the fun of it. Can I call this thing R of theta? Will it let me do that? Yeah, it doesn't mind that. the reason I said I wanted to do that is because do you understand that down here, then I could just say R of theta, you see that's still working? And now I can go up and change. You see I have a formula sitting there now that just finds the integral of whatever formula I stick up top.
Nice.
That's kind of fun, right? So now I can go up here and screw around with this and do something, you know, a little more nuts.
Still got to find the bounds though.
Yes, the bounds are no joke, and that's kind of the point on this. Is that's this kind of the non-simple part of this. But that's the other reason why the slider thing is kind of fun. Just because then you can slide around and kind of make sure that the graph is actually what you're after. Let's see. So I don't think I'll do this one, but I'm just sort of curious what it looks like. What if I said y equals the cosine of theta, square root of the cosine of theta? So let's see, how does that graph? Let's see, where is that? There we go. Did you notice I was like, what's wrong with this thing? So it starts at 0. That makes sense. Cosine of 0 is 1. The square root of 1 is 1, and 1 times 5 is 5. So it makes sense that 0, 0, 5 would be a point. And then it grows and grows and grows. That's kind of interesting. Why did it just pop down right there and just stop at 0, 0? What do you notice about the value I'm at? The angle, I'm at angle C. Where am I right now? You should recognize where that is. 1.6 is about what?
Oh, is it pi over 2?
You should have memorized that pi over 2 is 1.57. So at 1.57, the cosine of pi over 2 is 0. Oh, no wonder I'm at 0 then. The radius is 0. And then I went past this and it was like, there's no graph. I'm confused. Why is there no graph? Where's the
Did it just
graph?
jump and overlap again?
Maybe it's jumping and overlapping. That's not the case here. What's the cosine of an angle once I get past pi over 2? Like, what's the cosine of 2? Get your calculator out. Cosine of 2.
Negative.
Negative. Aha. Square root of a negative. So that actually doesn't exist. Like there's no graph. That's kind of weird. Isn't that fun? So that's why I couldn't find the dumb thing. So there's no graph. So if that's the case, cosine is negative all the way around to 3 pi over 2, isn't it? 3 pi over 2 you should have memorized as 4.71. So suddenly this graph should start happening again once I get past 4.71. So again, that's just kind of surprising. This is the intuition you need to like find where the graph exists. Now, this would be a good test question if I said, you know, what's the area under that curve right there from 0 to pi over 2? That'd be obvious what I meant. But the fun part to me about polar graphs is if you get cosine and sine into them, they close up and actually create a definable space. So I'm curious to see what's going to happen. So I'm almost to 4.71 and suddenly this should start existing again. So that's kind of fun. So I could say, what's the area of that? Now, if because I made this question up, I'm thinking, well, that's kind of weird. How do I just say from 0 to 2 pi and then not worry about the negative square root stuff? What's the easiest thing you could do? What do you notice about that graph visually?
You just do
Symmetrical.
half of it and then multiply it by 2.
Exactly. Symmetrical. I heard somebody say, yeah, we could just do from 0 to pi over 2 and then just double it and we get the answer and kind of not have to, you know, sweat or worry about what happens if I include those negatives. So but the point is does it make sense if I stuck this in the equation? The equation says to square that, right? So I'd end up taking the integral of 1/2 times 25 cosine. Well, I could actually do this one by hand. Does that make sense? But it's pretty rare. That's fine. Again, I just want to play for a second. And by the way, if you come up with something fun yourself, feel free to let me know. I'm just going to play for a second and try. And we want stuff that's got sines and cosines in it, just because that's what creates graphs that return on themselves. So I'm just wondering, you know, what if I threw like a cosine in here on top of it? Would that be fun? So appears to be. Yes, that is fun. What if I throw like a 2 in front of that? We saw that that kind of did fun things. Okay, that's cool. So we have a cartoon bomb now to find the area. But again, the area is a little confusing. You know, what do I mean? What if I said, it could be an easy question if I said find the total area of that shape, right? Because it's like 3 little chunks. And so there's 2 symmetrical ones on top. So I could do that and double them. And or maybe I could just, you know, did it take all 2 pi to graph this thing? Well, I don't know. Let's go take a look at it. So it actually started from 0 and then grew out, came back on itself. Where did it land back on itself? I don't know about you, but I don't recognize that. 0.77, anybody recognize that? Is that a known location? I'm thinking, oh, I don't know what that is. I don't know. And then, oh, it actually went down and made the bottom part of the bomb. So the bomb went from like 0.77 to 2.35 or somewhere in there. Again, those are unrecognizable locations, right? And then it completed itself. Oh, that's fun. What do you notice about how long it took to complete the shape?
It took exactly pi.
Looks like it took pi and we were done. And so if I keep going, I get no more graph. Therefore, it must be just landing on top of itself again. Isn't that kind of interesting? So if you just said, oh, I'll just go from 0 to 2 pi and I'll be done. That might have given you double the answer. Does that make sense? So I'd say, and I want to give you a second to think about this. Let's just say we wanted to find the area of that shape, kind of all 3 of the loops together. I could probably say that on a test if I, you know, and make it clear, if you will, or maybe like give you a picture and shade it, find the shaded area. I could say something like that on the test. That'd be a nice way to say it, right? Make sure you don't screw it up. But I just want to give you a second to get a head start. Notice squaring this and actually taking the integral by hand sort of feels out of the question here, doesn't it? Doesn't that feel like an extremely terrible idea?
It's cool when you graph the integral equation on your calculator because you can kind of tell the little areas that you're finding on there. It's like a little version of the same, different version of the graph, but like.
Are you saying you're doing that on your graphing calculator? Is that what you're doing?
Yeah.
Yeah, let's answer this one on the graphing calculator because I know what you mean, and that's a wonderful observation you just made. I want to make sure everybody else understands what you just said. So we actually saw that the whole graph, if you will, was done just from 0 to pi, and I guess we'd have to say less than or greater than to be perfectly precise. So part of me wants to just say, well, let's just do the whole thing then. Let's just go 0 to pi. I'm not super confident that this is going to work. Do you feel that way? I'm thinking exactly what Raymond was thinking earlier. Like, I think I need to part this out. I need to find, like, I want to find just kind of this over here, get an answer, double it, and then I want to go down and find, you know, this down here, and then, you know, kind of take over and do it myself. I'm a little worried that if I just say 0 to pi, it won't work. Do you think it will? Well, let's just stop and reason about this for a second. If you think about what we're doing, aren't we basically taking sectors and adding them together? So if we start from 0 and we go, okay, that's adding all of these sectors together, and so that filled that in. Then we jump over here. Isn't that just adding these sectors in? Actually, it didn't do that, did it? It went from here and then it went over here. So then it would be adding all of these sectors in, and then it got to here and started. Actually, I'm changing my mind. I think if we just go from 0 to pi, this is going to be, we're done. We found the whole answer. I don't think I need to chunk it up, but let's test that out. We have just enough time to kind of do that. So if I cheat on this and say 0 to pi, it says 9.8 for that answer. Let's see, 5, the thing is like 5 deep and 2 wide. Yeah, that's like 5 deep and 2 wide. So as a rectangle, 5 by 2 would be 10. But then that didn't include the little loop-de-loops on top. But then I treated the bottom as though it was a rectangle, not a kind of an elliptical looking shape. And so actually, I think that's working. I think that's the right answer. I think I found the area and I didn't have to really think about it much.
Yeah, that looks right.
Yeah, I think so too. So great, 9.817, game over. So, but let's do it. Let's do the little chunks and just kind of prove that to ourselves. So we have the same problem we had before, and it really helped to watch it grow. So it actually went from 0 to here. Again, notice that's a really interesting place because that place is where r is equal to 0. So it started there at angle 0. We'd have a radius of 0. Is that really true? Yeah, because notice the sine of 0 is 0. So 5 times 0 times whatever cosine is 0. So that'd give us a radius of 0. And then we were here again, and then we took off out here, and then we were here again, and then we took off out here, and then we were here again. So it was like 3 times we were there, right? So now suddenly I'm getting worried because we're saying, okay, well, you know, where are those intersections? Well, that would be where 5 times the sine of theta times the cosine of 2 theta is equal to 0, right? Well, fortunately, suddenly I'm thinking, okay, this isn't so bad. So sine of theta being 0 would do it, right? And that happens at theta equals 0, sine of theta, sine of 0, 0. And it also happens at 2 pi, in other words, after you've done a full lap. Or we could even say, since our problem doesn't go that far, at pi, doesn't it? Because that's when it got back. Isn't the sine of pi also 0 on the unit circle? Because the sine is the y coordinate, and isn't the y coordinate if you're over there at pi also 0? So again, we saw that happening. So that was kind of at the start and the end. But then notice we love this multiplication sign here because that means that there's another set of answers to this, which is where cosine of 2 theta is equal to 0. So unit circle, I'm thinking, where is the cosine equal to 0? Oh, that's right. That's here and here. Isn't that the 2 places? Cosine is the next coordinate. So there and there. So that means 2 theta would have to be pi over 2. Or theta equals pi over 4. And 3 pi over 2. 2 theta would also have to be equal to 3 pi over 2. So that'd be theta is equal to 3 pi over 4. Notice, no wonder I didn't recognize those. So these are kind of all of my answers. These are all of my, well, those are the important starts and finishes. Those are all the important places. And so let's go back and think about this. So this first one then, kind of that red area, I'm going to color it in red, really dark. Call that area 1. So that must be existing then from that 0 to that first pi/4 answer. Do you agree with that? From 0 to pi/4. Well, I don't have pi/4 memorized, so in a sense, I'm thinking to myself, well, no wonder I didn't recognize it. But let's just go see if that was actually true. See if we did our math right. So if I go over here, we said that was around, 0.77, and we were like, I don't recognize what that is, but let's go just type pi/4 in there. Oh yeah, 0.785398. No wonder we didn't recognize it, if you will. And so there's an answer. If I went from 0 to pi/4, that would take care of that little petal, if you will. Again, we're assuming they're symmetrical, and I think we can get away with that, but we haven't necessarily proven that that was true. Okay, then it took off from there and went around, but let's go get this answer really quick. So that's 0.371 for that area. And then this blue area, let's again color that in really dark. That's obvious what we mean. This is kind of area 2. So area 2. But we don't know what limits of integration to pick just yet. This is area 1. So let's go back to take a quick look at the graph. And so again, we think we know because we just did the math, but doesn't give me my slider back. By the way, watch this. Like up here in the top, notice I could go up here and say, let's start this thing at pi/4, couldn't I? In other words, you don't always have to start at 0. So I'm now saying I'm going to start at pi/4, and now let's go past that. So this thing went from pi/4 and then bam, right there. Boom, right there. So that's like 2.36, somewhere in there. Which answer was that? Was that the 3pi/4 answer? I think it was. I'm just guessing, but I think that was it, right? So if I said 3 times pi divided by 4. Aha, yeah. So we're going from pi/4 to 3pi/4. Assuming that we could not take the integral. So let's see what this says. Pi/4 to 3. It's kind of fun to be able to type those in exactly. So we got 9.075 for that. So the question is, did that give us the same exact answer? If I take 2 3.71s and add that to 1 9.075, I get the same exact answer, don't I? We got a second ago. So I want to show you quickly, and if you need to leave, that's perfectly fine. But I want to just quickly stop sharing this screen. What am I doing? Stop sharing the screen. Share my regular screen. Bring up the regular graphing calculator. And let's cheat and find this area using the regular graphing calculator. So I've got to go into mode. It's not mode. What is it? It was mode. I gotta go down here and change this to polar. No, I don't. So I'm cheating and using the integral function of this calculator. So I'm saying, okay, what integral are we taking? We're taking the integral of 1/2 times our equation squared, which was 5 times the sine of theta, which I can just call x, times the cosine of 2x. So notice I actually don't need to be in polar. I need to be in polar to graph it. And so I started a parenthesis, I closed it, I squared it. And so there's my, notice this is not the graph of the shape. This is just, let's see, this went from 0 to 2 pi. Let's just hit graph and see what happens. I'm probably in some weird mode. I wish I hadn't done that. So before you hit graph, I should have went to window and say, I want X minimum to be 0 and Y minimum to be pi, because that's all the further I need to see. And since our area was like 9, then I'm going to say, I don't know, I guess I'll try -10 to 10. So this is not the graph. This is a function that tells us the area. Does that make sense? So what I think Ben pointed out is, notice they're all positive. Do you see how there's no negative areas here? So what I think Ben was saying is, there's the area we just got a second ago that was it 3.71? I can't remember. 0.371. I wrote 3.71 minutes. So this is the 0.371 and this is the 9.075. So now I can cheat and say, second, calculate what is the integral from, let's first try to find that little chunk right there. From 0, that's my lower limit, enter, what's my upper limit? Second pi divided by 4. The good thing about your graphing calculator is it shows you what area you just found. Notice that kind of proved we got pi over 4 right, because it actually stopped where it was supposed to. That's the same 0.371 we just got a second ago, so that's kind of fun. And to cut to the chase, if I say second calculate, what is the area under the entire thing from 0 all the way to pi? Now it should fill in all 3 of those shapes. Right now it was filling in that first one again, and now it's filling in the rest of it. And that gives us the same answer we had before. 9.817, cool. So you're actually seeing a visual representation of each of those little loop-de-loops. So that's kind of fun. That's the one advantage to the clunky version of your graphing calculator doing this. So I'm glad I did that really quick, because it's like you can't do that in polar mode. I don't think you can. Is that true? Actually, I guess I don't know. I'm gonna find out right now. Feel free to boogie, because I'm going way over time, but let's go down to polar mode, try to graph this thing really quick in polar mode. See if that integral button will work in polar mode. So I'm just graphing the graph, which was 5 times the sine of theta, close that parenthesis, times the cosine of 2 theta, close that parenthesis, and if I hit window, notice we discovered already that you don't need to go a complete 0 to 360 or 0 to 2 pi. So I'm just going to go from there, and then it has a step in it. And the window is -10 to 10. I think that's going to be okay. No, it isn't. That's the same window I had before, so that's not a good window. So I'm going to say zoom standard. So, okay, that worked. And then I want to go second, calculate. Can I go, notice there's not an option to find the integral. You see what I mean? I'm not surprised, because it's kind of a weird weird thing. It's like there's an option to cheat and get a slope of that curve. That I could cheat, but there's not an option for me now. It's too complicated to cheat and get an integral. That's kind of cool to know. Didn't know that. So I'm just going to fix my notes. If you have something you want to stay after and ask me, please do so.
All right. Thanks, Doug. Bye.
Good comments, Ben. See you later. See you, Alyssa.
Hey Doug, I actually had a question about the 12.1 calculus with parametric equations homework.
Sure.
On question 4, it asked for a point of tangency, and then it asked you to give the equation of the. It might have just asked to give the equation of the line of tangency. So I was easily able to figure out the slope by putting dy over dx, but then I had a hard time finding like the b constant, and I actually kind of just graphed it in Desmos, and it was pretty easy to like find the move the line until it touched the graph and find the constant by like kind of cheating that way, but I never figured out how to do it algebraic.
Yeah, let me pull that. Let me see if I can pull it up. Was it in the second chunk of homework? The
Yeah,
calculus?
12.2 or 12.1, sorry, second one, the calculus with parametric equations.
Yeah, so you had no trouble with the kind of dy dt over dx dt.
Yeah, no,
Add
that
your
fine.
slope. So the key is if you have your slope, let's say the slope is 6, and you're like, oh, sweet, I know it's y equals 6x, right?
Right.
And then it's like plus, I don't know. Well, the only way you're going to know is if you have a point that you know works to plug in. And don't you? Like in the problem that I just shared, I have share on, don't I? No, I don't think I do. So in the problem I just pulled up right here, do you see how it says at t equals -1? Well, couldn't you put t equals -1 into this? And 3 times -1 is -3. -1 to the 7th is -1. So you have the point -3, -1. Well, that point has to work in the equation. So you know the equation is y equals 6x plus something. We'll plug in -3, -1. That has to work in that equation since the line goes through that point. That's going to figure out what that unknown is without having to guess.
Okay, that makes sense. Awesome. Thank you, Doug.
Good question. How about you, Cheyenne?